Hello, so in this video we'll be looking at Maxwell's equations. Maxwell's equations are descriptions of how energy associated with changing electric and magnetic fields can travel. It describes changing in electric and magnetic fields, how they relate to each other, and we'll see that if we look at how energy contained in these changing fields can travel, we'll end up with a wave equation for the electric and magnetic field. Crucially, a wave equation which describes a wave whose speed is absolute, not relative, unlike the speed of many other things we're used to in the universe. So I'll get quickly cracking on with the mathematics. Before we look at Maxwell's equations, it's worth saying for this video I will not be going into at least the foundation of the maths, so ideas in vector calculus, which is the language used to write Maxwell's equations, in any great detail. There are many great texts on that. We'll just be getting a visual understanding for operations in vector calculus before using them to play around a bit with Maxwell's equations to get out from his four equations the idea of an electromagnetic wave. So, as mentioned, we're going to do a quick crash course in the maths required for Maxwell's equations. So we'll be looking at the curl, the gradient, and the divergence of fields. If those terms are familiar to you, wonderful. If they're unfamiliar, don't worry. We will cover all of these in great detail. Well, I say in great detail, I mean in, very approachable detail here. Even though, at uni this would be, almost a module to itself. So we start really with the bit of vector calculus we're concerned with, which is kind of generalising differential calculus. So differential calculus concerns how a quantity which depends on some input, will change when we change the input. Now, if we changed the input a little bit, the quantity would change a little bit. And we could see, well, if we divide the change in the quantity, so in other words, the change in the output, by the change in the input, we'll get an average idea for how the quantity varies as the input varies over some domain. However, if we want to know how the output, so the quantity we're interested in, varies at a particular point with a specific input, then the change of the input we have to consider is infinitesimal. And this leads to the idea of looking at the infinitesimal change in the output divided by an infinitesimal change in the input. And this ratio is exactly what the derivative is. So we're familiar with kind of derivatives. If you do A-level maths, you'll learn a lot about derivatives in your first year. And if we look at typical functions, like y equals x squared, well, the input there is x and the output is y, so y is the thing we're interested in. But y, well, if we look at every possible value of y, we can put all those values on a number line, essentially a one-dimensional line, meaning we can consider functions like y equals x squared a one-dimensional field. It's one-dimensional because the y-axis is itself one-dimensional. In other words, the output, the thing we're interested in, doesn't have more than one component, so we can contain all the information for each output as a single number, and we can put these numbers on a number line. But also we have a field because the output, well, because for along this line where we've placed all our outputs, at any point along that line there will be a specific output. There are no values of y missing, say in the function y equals x squared. At least if we're, allowing x to stretch over a large enough domain. You might go, well, we can't have negative values for y, and providing x is a real number, that's true, but at least in terms of positive numbers for y, every number of y has a matching kind of input x. So y equals x squared is an example of a one-dimensional field, as are the kind of functions you'll be quite used to seeing in maths at A level and before. And for a one-dimensional field, we can only really consider one type of derivative, which is why we don't really talk about types of derivatives in A-level maths. We just talk about, there being a derivative, or in some cases, at some points, the derivative being zero. So for a one-dimensional field, because the output for any input is a single number, we can, when we're thinking about how much the output changes, we can just go, well, does the output number get bigger or smaller? And this leads to the idea of the gradient or steepness of the curve, which represents our functional 1D field. So for all 1D fields, we can define a gradient. Now, if the output, so the thing we're interested in, has more than one component, so in other words, the output doesn't return a number, it returns a collection, if you like to be using computer science language, you could say returns a tuple of numbers. In other words, returns a vector, for example, the electric field, where the electric field has at each point in space a vector describing this field, then we can do more stuff. We can define more types of derivatives, but the idea of the gradient can also still be perfectly defined. So the gradient is a derivative operation which applies to fields of any dimension, including 1D fields, but does apply to fields of larger dimensions as well. But the next two types of derivatives we're going to look at won't apply to one-dimensional fields, but will to the electric and magnetic fields, because the electric and magnetic fields exist across space-time, so when we give it an input, that's a position in space, we'll get an output with three components. The field along the y-axis, the field along the z-axis, and the field along the x-axis. So for an electric field, say, the output is a tuple of three numbers, so it's a three-dimensional field. And so we can start to define for this field more, if you like, exotic types of derivatives, which describe how the field is changing when we change the input infinitesimally. So for these next two types of derivatives, we need to consider something called field lines. So at each point in space, if we've got a field, we can consider how strong that field is, and we can also consider what kind of direction that field is pointing in. And so at each point in space, we can place an arrow. Where the length of the arrow corresponds to the strength of the field, and the direction the arrow points in tells us the direction the field is pointing in. And these arrows are called field lines, because they show us the direction of the field, and they also tell us about kind of, if you like, the strength of the field. Now, one way you can talk about the strength of the field is by using field lines of various lengths, but this can get very graphically confusing. A better way often is to describe the strength of a field by how close the field lines get together. That way we can have a field where the field lines all have the same length, but we can learn something about the strength of the field by considering how close the field lines are together. And this brings us on to our second type of derivative. So for a field which is two-dimensional or of larger dimensions, the output contains at least two numbers, meaning our field line will have at least two components, and therefore we can meaningfully talk about the kind of angle one field line is pointing relative to another. And therefore we can start to consider kind of field lines which are kind of various angular distances apart. And then if we look at the direction of the field for field lines which are, angularly displaced from each other, then we can identify regions in the field where the field lines are kind of converging, which corresponds to the field increasing in strength. We can also identify points where the field lines are kind of trying to diverge apart, corresponding to the field getting weaker. And for divergence, we use the upside down triangle symbol, but we also use a dot between this symbol and the field we're finding the divergence of. So if there's no dot, we're finding the gradient of a field. If there is a dot, we're finding the divergence of a field. Now, the reason why this idea wouldn't really make sense, the idea of a divergence, if we consider the 1D field, is because if we look at a 1D field, well, the output for a 1D field is a single number, and as we said, we can displace these single numbers on a number line, and so all these numbers just lie along the same line, and therefore kind of the field lines would point in the same direction. So for a one-dimensional field, the divergence of that field would always be 0. So that's why it would be kind of pointless to try to apply the idea of a divergence to a one-dimensional field, because by definition the divergence would have to be 0. So that's why we need more than one dimension if we're going to talk about the divergence of a field. It is worth saying that because of the way that we it's you could kind of mathematically make this a lot more complicated and talk about, well, if we had a one-dimensional field, would there be some way to transform the idea of the divergence into the gradient of that field? We won't be going there though, this is just a kind of crash course, so this will do for our purposes. The second type of derivative which we can apply to a field with more than one dimension, which wouldn't work for a field of one dimension, is the idea of the curl. And the curl again makes use of the relative angle between field lines, thus it wouldn't work for a one-dimensional field. And the curl concerns the idea that the field lines might be orientated in such a way that kind of spirals, or if you like vortices, start forming within the field as shown by the field lines. And when the field lines look like they're beginning to kind of spiral, or kind of like field lines are consecutively beginning to form a curve, we say that the field has a curl because it's beginning to kind of rotate. And the kind of physical meaning of a field that has a non-zero curl is that the direction of the field depends not depends on your angular position relative to the source. Um, it depends not only on how far you are from the source, but also on your angle relative to the source. So, for example, things like the force generated by a bar magnet is an example of a field which would have non-zero curl because, say, for example, your angle is such that you're kind of orientated with the north pole of a magnet, you'll feel a substantially different force to if you're orientated kind of such that you're facing the south pole of the magnet. So it matters what pole you're facing. So the field has curl. It has some kind of rotational dependence. I should say angular dependence. However, you won't often see curl in regards to the kind of fields representing forces which you're used to seeing in things like A-level, because in A-level you're looking at forces generated by point particles which tend to be radial. That is, they tend not to depend upon angle. Examples are the gravitational force generated by a point mass, as defined by Newton's gravitational equation. Also, the electrostatic force generated by a point charged particle, as defined by Coulomb's law. All these forces are radial and therefore will have zero curl. Now, the two types of operations we'll be concerned with, the two types of derivatives we'll need for Maxwell's equations are the curl and the divergence. We'll need the curl because the curl will actually tell us about the dynamics of electromagnetic waves. When we're talking about when we're talking about dynamics, we're talking about how fields change, so the time derivatives. And the time derivative of the magnetic field relates to the the curl of the electric field, and the time derivative of the other field relates to the curl of the first field. So the way that the fields are intertwined is by relating the time derivative of one field to the curl of the other field. So it's really the curl that kind of electric and magnetic fields are kind of coupled together. We'll also be making use to get to a wave equation from Maxwell's equation, the idea that if the electromagnetic waves are travelling in I should say, because we don't want to prior assume that there will be waves, so I should say if the electromagnetic radiation is travelling in a vacuum, then the divergence of the electric and magnetic field is zero, and I'll talk more about why that is when we get to Maxwell's equations. So this has been a very quick crash course in div, curl and grad. Don't worry if you're not too sure of the exact details. We're saying we haven't gone through any of the computational aspects because actually we don't really need them. We just need to understand what these kind of operators really are, and in fact going through the computational details will probably just distract us needlessly. So I'll kind of end this part of the video there, and we'll now be moving on to Maxwell's equations. So having talked about the div, curl and grad operations, we are now at a place to talk about Maxwell's equations. Now it's worth saying Maxwell's equations have a reputation in popular culture for being very mathematically complicated. The reason for this is because the explicit mathematical descriptions of grad curl, and div are rather long and bulky. So if we wanted to have a field and calculate the actual value for, say, the curl of the field, that would involve a fairly bulky calculation. And because Maxwell's equations referred to grad, curl, and div, well, they referred to div and curl anyway. This means if we're going to write Maxwell's equations explicitly out in terms of the components of the electric and magnetic fields, then yes, the equations would be incredibly bulky and would be rather daunting. However, if we're not worried about the precise mathematical computational description of these derivative operations, then really all Maxwell's equations boil down to is talking about how the field lines of an electric and magnetic field can kind of like diverge or converge, and also how the electric or magnetic field can have some angular dependence or not. So using our visual understanding of these operators, Maxwell's equations is actually incredibly simple. Now there's two types of kind of like Maxwell's equations, if you like, or two forms of writing them which we could use. The first of which I shall call the vacuum equations. I've heard that used before. I'm not sure if it's technically correct, but it gets across the crux of when you would use these. So these equations describe electromagnetic radiation if this radiation is moving through empty space, so isn't being affected by matter. Now, it could in principle talk about electromagnetic radiation travelling through that matter if that matter had no effect on the radiation. However, because physical matter is made up of a nucleus and electrons, well, atoms of physical matter are made up of of a nucleus and electrons. In physical matter, you have moving negative charges, so your electrons, even if they're just moving locally around their own atom. And since you have moving electric charges, these electrons will interact with an electric or magnetic field which they encounter. So physical matter will generally respond in some way to electromagnetic radiation thanks to electrons. And it's this response actually causes things like the refraction of light bending as it passes into a new medium with new matter content. So, for practical purposes, we can really only use the vacuum equations when either light is literally travelling through empty space or is travelling through space with such a small matter density that the light, to a good approximation, barely interacts with anything. Now, sorry, if you're interested in experimental physics, you're going to be quite interested in the material equations, which are much broader than the vacuum equations, and they describe how electromagnetic radiation travels through physical matter. And this is a very active area of research, particularly a massive haven for experimentalists. Because we can learn a lot about physical matter through how light interacts with it, but also we can design matter in such a way that light will do some very unique things. And we can consider different states of light, we can bring quantum mechanics into the picture, so it's a very rich field. So the material equations have plenty of uses. However, for our purposes, we are interested in trying to derive the idea that there is some maximum universal speed. There is some finite speed which nothing can move faster than, and it will turn out that this speed relates to the speed of electromagnetic radiation moving through outer space. Because when the radiation moves through kind of matter, due to interactions with matter, it's slowed down, and therefore can't move at its maximum hypothetical possible speed. So as we're interested in how quickly light can move or how quickly information can be transferred, not on how much the transfer of information can be slowed, we're interested in the vacuum equations. We're not going to be using the material equations. And the vacuum equations describe the electric and magnetic fields in terms of divergence and curl. So if we look at divergence, the nice thing about the vacuum equations is not the case if we're looking at material equations, but if we're looking at the vacuum equations, the divergence of both the electric and magnetic fields are zero. And what this means is that, the fields aren't doing what you can see the field lines doing in that cube. The field lines are not getting farther apart. The field lines are essentially remaining parallel. And what that tells you is that across the region where this electromagnetic radiation is moving, this electromagnetic radiation isn't becoming stronger or weaker. And in terms of the context of waves, this will correspond to an electromagnetic wave when travelling through the empty space, not increasing or decreasing in amplitude. So that's the meaning of this kind of divergence being zero. Essentially tells us our electric or magnetic fields can't get weaker, which isn't too much of a surprise because these fields are moving through empty space, so that's not really a massive shock. What is more interesting, one might say, although we will use the idea of the divergence being zero as a crucial thing when we're trying to show that these four equations here will result in wave equations. So, we will need the idea of the divergence being zero. But in terms of the dynamics, a much more interesting thing is to consider the curl of the fields. So an important thing to note here is that we can clearly see the time derivative of one field is related to the curl of the other field, and that kind of entangles the fields together. And physically, I suppose, you can think of this as essentially saying, like, for example, let's take, for example, the curl of the electric field is equal to minus the rate of change of the magnetic field. So the top equation in our kind of right blue box. Well, if we look at this equation, what this is saying is essentially if our kind of like magnetic field starts changing very quickly, then our electric field will start to gain some kind of curl and will cease to be to a good approximate, and will cease to be a kind of radial field to a good approximation. So it's telling us that essentially if the magnetic field starts oscillating very quickly or changing very quickly, the electric field can no longer really be considered to be radial at all, and we have to abandon Coulomb's law for the kind of electric field. And so it kind of allows, well, if you have a changing magnetic field, for the electric field to do something much more interesting than to just be a radial field like the one described by Coulomb's law, but to start being more geometrically complex, allowing for patterns like waves. Now, the other thing to note is that in our bottom of the two curl equations, we have mu naught and epsilon naught. Now, mu naught and epsilon naught are fundamental constants to the universe. They refer to the resistance electromagnetic radiation feels when it's trying to travel through empty space. Now you might think, well, it will feel no resistance. So the values for these constants, mu naught and epsilon naught, should be 0. However, by resistance we mean something trying to slow down electromagnetic radiation. And so if we said that the radiation encountered no resistance, then what we would mean really would be that the radiation would be able to travel at infinite speeds. And, in Newtonian physics we assume information and light, including, can travel at infinite speeds. And so we would assume that the resistance would be 0, and we would take mu naught and epsilon naught to be 0. And an interesting thing happens if you would take these things to be 0, or in other words, if you would consider light to have an infinite speed. Because according to Maxwell's equations, if mu naught and epsilon naught are both 0, so in other words light is travelling at an infinite speed, then the curl of the magnetic field is 0. So we would have the curl of the magnetic field is 0, but we know from one of Maxwell's equations the divergence of the magnetic field would also be 0. And those two things put together would mean that kind of like the magnetic field would become a kind of irrelevant concept and end up having no physical meaning, because we could physically then just consider the magnetic field to be 0. But then if the magnetic field is 0 according to our equations, the curl of the electric field is 0, and we can then make a similar argument about the electric field being kind of meaningless. And so essentially Maxwell's equations go, well, if light is moving at an infinite speed, we can't really have light because we can't have an electromagnetic wave. Essentially, there's no physically meaningful electric or magnetic field that could travel through the vacuum. So, bizarrely, there's a link between the idea that the speed of light is finite and that light can travel through a vacuum. Those two concepts are related. And we'll actually see mu naught and epsilon naught appearing when we try to find an expression for the speed of an electromagnetic wave. So we'll see explicitly that kind of like, if you take mu naught and epsilon naught to be approaching 0, c will go to infinity, and there is a very specific correlation between c, the speed of light, and mu naught and epsilon naught. So these are Maxwell's equations. Now we have Maxwell's equations, and we have discussed them briefly. We now want to do something to get a hopefully fairly independent equation for the electric field associated with electromagnetic radiation in a vacuum, and also the magnetic field for the magnetic field in a vacuum. Whilst it explains a lot of physics if they're coupled together like they are here, it makes deciphering properties of this electromagnetic radiation very difficult. And we also have foreknowledge that what we'll end up with is an electromagnetic wave, so we want to try to get towards a wave equation. So we'll be, doing those things, both trying to get, say, an expression, for example, just for the electric field, and also try to get this expression in the form of a wave, if at all possible, on the next part of this video. So now we've introduced Maxwell's equations in terms of the divergence and curl of electric and magnetic fields, we can get on to finding a wave equation. So, a good question to ask, well really the only question to initially ask I suppose is where to begin. Well, we know, we have the benefit of foresight, I'm not sure if Maxwell had a hunch, but we know that we're going to end up with an equation of an electromagnetic wave. And if we think back to the wave equation for a string, which we can think of as almost a one-dimensional field, which we mentioned, and we derived the equation extensively in the last video, we saw that the wave equation for a 1D field related the partial derivative of the field, well, the second order partial derivative of the field with respect to a spatial coordinate with a second order time derivative of the field. So a wave equation should contain a second order time derivative of a field. And this should still apply to, any fields in space or even in space-time, because we only have one dimension of time, so when we're generalizing a one-dimensional field to a three-dimensional field, we're not doing anything to change the number of time dimensions, if you like. So if we had a second-order time derivative for a 1D field wave equation, then we should also have a second-order time derivative for our electric and magnetic fields if they're following a wave equation. So we want to start to introduce somehow a second order derivative of a field with respect to time. And our curl equations already contain derivatives of field with respect to time, but to get a second order derivative, we'll have to differentiate both sides with respect to time, both sides of the equation, and that will leave us on one side of the equation with now a second order derivative with respect to time. And that's exactly what we've done here. We've in the blue box, we've essentially taken Maxwell's equation describing the curl of the magnetic field, and just differentiating both sides with respect to time, you immediately can state this. So this has to be true, because this comes directly from Maxwell's equations. However, we're doing this because it introduces a second order time derivative, because we're guessing our solution might well be in the form of kind of describing an electric and magnetic wave, for which we need a second order time derivative. The question is now how to go any further. Well, at the moment we still haven't really completed our promise of having an equation for the electric field, which is to at least an extent independent of the equation of motion for the magnetic field. Because our top equation here still involves magnetic and electric fields. However, we saw that Maxwell's equations would relate the time derivative of the magnetic field to an electric field. So we can immediately see that if we could somehow switch the order in the first term of the curl and the time derivative operator, then we could have the first kind of left-hand side of our equation being an equation in terms of the electric field, which would also therefore mean that our entire equation would end up being an equation in terms of just the electric field and not the magnetic field. So we want to switch the order of the curl and the time derivative. Now, if we weren't doing a playlist on relativity, I would probably just do that without mentioning anything odd about saying we can do this. However, given this is a playlist on special relativity, it's worth noting we are assuming here that time and space act kind of independently, such that, the order in which we apply derivatives in time and space doesn't really matter, providing one derivative is a derivative in terms of space and the other is a derivative in terms of time. Now, the paradox really is that by assuming this, we'll end up with a wave equation which will tell us that the speed of light is a universal constant, but that very statement that the speed of light is a universal constant itself indicates that time and space are intertwined, thus bringing into question whether we can actually do this switching of the time derivative and the curl in the first place. I.e. whether the curl and time derivative are indeed independent operations. Now, I will probably at some point have a video where I go through some kind of the nitty-gritty of things that I have glossed over, but it's worth saying that yes, we can do this. The details of which I will cover in a future video on this playlist. But for now, to keep this video at least reasonably short, particularly given the last one was fairly lengthy, I'm just going to go ahead and say we can swap the order of the time and curl operators. And when we do this, we're going to end up with, on the left hand side, the curl of the rate of change of the magnetic field, but we can use now Maxwell's equations that go where the rate of change of the magnetic field is itself described as the curl of the electric field. And so now we have two curl terms on the left hand side of our top, the very first equation on this slide. So how do we deal with two curls? Well, you can use vector calculus to prove that this statement is true for any vector field if. It's true by definition, it's true based on how we define all the terms in this expression. So what this rule, or I should say identity, because it holds for all f, really says is that the curl of f is equal to the gradient, so in other words, kind of the steepness of the divergence of f minus something that is essentially the generalization of a second order derivative in space, but to 3 dimensions. And this generalization is called the Laplacian operator. So we have minus the Laplacian operator times f. Now the Laplacian operator has many symbols. You can have it being written as the upside down triangle squared, because you know you can kind of formally think of it as well something kind of equivalent to the divergence of the gradients of a scalar field. There's many ways to think about the Laplacian operator, but sometimes it's also represented as a triangle the right way up, but I'm not doing that because a triangle the right way up often in physics means macroscopic changing. It's a symbol delta, so I don't want to be doing that. So the Laplacian operator, this upside down triangle squared, is just a generalization of a second order space derivative, but taking into account that we have lots of space derivatives because these waves move in 3-dimensional space rather than the 1-dimensional motion allowed, say, for particles that make up a string. And when you use this vector kind of identity, we can then apply this to our top equation, but with a top equation now involving the curl of E, thanks to our Maxwell's equations. And when you do this, it's worth saying that, well, the curl of E will, by definition, have to equal the gradient of the divergence of E, but we said the divergence of E is 0, so the gradient of the divergence of E is going to be 0, and then you'll have minus the Laplacian operator times E. And then, once you've gone through that, you'll then end up with a wave equation for the electric field, which relates second-order space derivatives. I say derivatives because there are many spatial dimensions to worry about now, with a second-order time derivative, causing them to be proportional to each other. So we do indeed have a wave equation for the electric field. And you'll see here the kind of constants of proportionality, which, if we think back to our wave equation for kind of material waves, is related to the speed of the wave. But for the electromagnetic wave, therefore, the speed is given in terms of universal constants, mu naught and epsilon naught. And therefore the speed of this electromagnetic wave is going to have to be a universal constant. So we've essentially derived the principal result of relativity, and we'll discuss this briefly on the next slide finishing this video, and then on the oncoming video we'll talk in detail about the idea of space-time that emerges from this rather bizarre consequence of Maxwell's equations. So we've got to a wave equation in terms of the electric field. Now, I did it in terms of the electric field rather than the magnetic field of the electromagnetic wave, because matter tends to respond to the electric field. The reason being is, although matter can respond to magnetic fields, it responds to magnetic fields very slowly. And so, if the magnetic field is actually changing very quickly, then the matter can't actually keep up with the very fast changing magnetic field, and the matter just sees the magnetic field as having some kind of constant average value. So if we look at electromagnetic waves where the magnetic field changes quite rapidly, so fairly high frequency waves like visible light, the kind of like atoms in a solid sample which encounters the light beam won't really notice a changing magnetic field at all. To them, the magnetic field will change so fast it will be as if it has some kind of constant average value. And because this is a wave, that kind of like average value will be essentially zero. Although if we're, considering the energy the magnetic field departs, that might be significant. Because the energy depends on, squaring displacement. So we will get some non-zero average energy associated with the magnetic field. But if we look at the wave itself, if you take the average of the displacement, you just get zero. So matter for a high frequency electromagnetic wave wouldn't really notice the magnetic part of the electromagnetic wave. It would notice the electric field, however. Hence it's the electric field which is often important. So often in the optical properties of solids, for example, even when you use the material equations, you're concerning yourself with the kind of material version of the electric field, which is called your displacement field D. You're not really worrying about the magnetic field much. So it's really the electric field, for example, that's responsible for refraction. By showing the unity of physics, electric fields and bending light might sound distinct, but they're very, very connected. But when we looked at Maxwell's equations, we saw that we end up with a wave equation for the electric field, but let's be a bit more specific, particularly how we know that it's a wave equation. Well, this is the equation we had for our electric field, with our universal constants mu naught and epsilon naught present. Now, in the last video we spent a fair bit of time using Hamilton's principle of least action to derive the wave equation for a oscillating violin string, and then we generalised that to talk about, a more general wave equation, and thus kind of talk about how we describe waves generally. But now we were looking at waves to do with displacement along one spatial dimension. So our waves was described by a function y, and as we said, a function can be considered as like a one-dimensional field. So before, what we had when we looked at a string was a wave equation, but for a one-dimensional field. If we have a field of higher dimensions, assuming we're still keeping one of time, the only thing that changes is the single second order partial derivative, which corresponds to just changing, one value associated with the input, now becomes instead a Laplacian operator, which is essentially the generalized version of a second order derivative, in space anyway. So we have the Laplacian operator instead of a second order derivative, but apart from that everything is the same, and since we are talking about a general field, I've used F for our field rather than Y. So comparing these equations, we clearly see that the electric field has an equation of motion that makes it a wave. And if we now compare the two equations very closely, we can see that the 1 over v squared would have to equal mu naught epsilon naught. And so, rearranging a bit, we can say that v for the electromagnetic wave, which has the symbol just c, because this speed is very special, is just equal to 1 divided by the square root of epsilon naught mu naught. And as I said before, if you take mu naught and epsilon naught to approach 0, c will approach infinity. And equally the reverse is true. If electric and magnetic fields can't travel through empty space kind of at all, at any velocity, i.e. we set c equals to 0, then we would require epsilon naught and mu naught to be infinite. And I would encourage you to look back at Maxwell's equations and consider why setting mu naught and epsilon naught, or even just one of them to infinity, would result in the electromagnetic radiation not being able to travel through empty space. But I'll leave that as an exercise for you. As I say, we're concerned with our universe where the speed of light is definitely not 0. And because these mu naughts and epsilon naught is just universal constants, we can get them by kind of like experiments fairly easily. And when you do that, you can calculate a theoretical prediction for the speed of light, and then you can look at visible light, and by looking at how long it takes to do a round trip and the distance of the round trip, you can get a value for the speed of that light beam. And indeed, visible light does move at this speed, which seems a very bizarre coincidence, unless visible light is an electromagnetic wave with an electromagnetic field, as described by the kind of wave equation we see here. There are other indications that visible light is an electromagnetic wave on top of that, but this is kind of the main one. It'd be rather coincidental if light just happened to have the speed of an electromagnetic wave, but itself wasn't an electromagnetic wave. Now, because mu naught and epsilon naught are constants, that is, they're agreed by all observers, it appears we have the speed of light in a vacuum, or in other words, the speed electromagnetic radiation can move through empty space, being a universally agreed upon value. So the speed of light seems somehow absolute, which is the bizarreness of this result. These electromagnetic waves have an absolute speed, unlike any other waves really in the universe. Or at least any other fairly tangible waves, at least if you can consider light tangible. In a sense it is, but in a sense it's very obscure indeed. However, here I'm going to start to be a little pedantic by what I mean by all observers, because that isn't completely technically true. And the reason it's not completely technically true is that this result, although true, does guarantee that the speed of light is a constant. This result depends on Maxwell's equations being true. And Maxwell's equations are true for all observers who are not accelerating, at least accelerating relative to the light beam or the electromagnetic radiation. If an observer is accelerating, we can't immediately trust Maxwell's equations anymore, so the speed of light can still be relative for accelerating observers, but at least for all observers who are not accelerating, no matter what their velocity, they will agree on the value for the speed of light in a vacuum anyway. It's worth saying we will probably come onto accelerated effects kind of towards the end of this playlist, because, well, it's because there's an interesting application with light, because empty space we said is empty in that electromagnetic radiation won't interact with anything. But we know that even if you have a space which doesn't contain, any particles or any radiation, it's not really empty. It still contains quantum fields, just quantum fields which aren't in excited states. However, if you're accelerating, you might well disagree with that statement and start to think that these quantum fields are actually in excited states and therefore start to see light and photons, which a stationary observer or an observer that is at least not accelerating wouldn't see. This kind of effect also really ramps up if you're kind of changing your acceleration drastically, such as if you're getting close to the event horizon of a black hole. Because there your changing acceleration can be quite huge, and you would start to detect a huge amount of radiation in what other people might just consider to be empty space. And this leads to the idea that a black hole, or the event horizon anyway, some kind of firewall. It's essentially filled with really hot radiation. We might talk more about that some point in this playlist. If I do one on general relativity, we definitely will. But there's many theories around black holes. So it's worth saying with all equations in physics, always be at least semi-skeptical of them. But at least for our purposes, as long as we're ignoring acceleration, Maxwell's equations can always be trusted, and therefore we can always rely on the speed of light being itself a universal constant, although derived from more fundamental universal constants. So that's this video. In the next video, we'll talk about how the idea of the speed of light being constant leads to, the idea of a space-time interval and the notion of space-time. And then the video after that, we'll talk about four vectors, the geometry of space-time, where we'll explore hyperbolic geometry in detail, and that will lead us to Lorentz transformations and time dilation. So that's where we're going, but I hope you've enjoyed this video, which is journeying all the way from the rather pleasant realm of, electric and magnetic fields, even to the realm of firewalls and black holes. So hopefully see you for more soon, and I hope you enjoyed this content so far, at least on this playlist, and hopefully will enjoy the videos to come.